At some point during your time in Maplestory, you've probably asked yourself, what am I doing with my life? Is this the optimal training spot? Are these the most efficient monsters I could be killing right now? To answer questions like these, you'll have to know the truth. To get an idea for what I'm talking about, consider the following case. Level 10 me against a level 2 blue snail. This is a good example because since my level is greater than the snail's level, and since the snail has no defense, my displayed attack range is exactly the damage that will be inflicted to the snail during an attack. This wouldn't be the case if either of those two conditions were broken. Now, you might think that we could just average my attack and divide the snail's HP by that value to get the average number of hits. That would be wrong, and to see why, let's see what actually happens when I kill the blue snail. What you just saw is a probability tree. It is the mathematical language underpinning all of Maplestory. For any character-monster matchup, there will be a unique probability tree. Ultimately, it is this object that must be used to obtain the true average number of hits needed to kill the monster in question. So let's see how that works, continuing with our example. This is the full hit tree diagram for the blue snail. It shows all possible ways that the blue snail can die. For example, in the clip shown before, I first begin by dealing 5 damage to the blue snail, taking us from 15 HP to 10 HP, so the number in the box represents the HP of the monster after each hit. And then for the second hit, I deal 6 damage, followed by dealing 4 damage, although at this point, any hit would do, since my minimum attack is 4. As a reminder, my attack range is given by the set of numbers 4, 5, and 6. Now, even just looking at this, we can see why our naive guess of taking the average of the attack range wouldn't work. As you can see, there are many times where we get the kill in 4 hits instead of 3 hits. What this means is that our average number of hits needed to kill the blue snail has to be greater than 3, because there are many possibilities where we end up killing the blue snail in 4 hits. So this suggests that instead of taking that naive average, we should instead take an ensemble average over all possible paths. We'll call the average number of hits needed to kill the blue snail n bar, and this is going to be equal to the sum over the number of hits weighted by the probability that the kill occurs in that number of hits. At this point, the natural question to ask is, what is this function p of n? What are its output values? Well, immediately we can say that the probability of getting a kill in 1 hit is 0, because there are no orange boxes on the first level. Orange boxes indicate where kills occur. Since no kills occurred in the first hit, the probability of getting a kill in 1 hit is 0. The probability of getting a kill in 2 hits is also 0. There are no orange boxes on the second level from the top. And so there is never a case where we can get a kill in 2 hits. Next, we need to find out the probability of getting a kill in 3 hits, and even 4 hits after that. And to answer that, we need to find the probability of one instance where we get a kill in 3 hits, and then add over all the times where that occurs. So let's see, how does this work? In Maplestory, the probability distribution for actually hitting a value in the attack range is uniformly distributed. So what does that mean? Let's call an element of the attack range little r, so that 4, 5, and 6 are elements of the attack range. What this means is that the probability for hitting some value in the attack range is 1 over the size of the range. This is just a uniform distribution. So in other words, there are 3 values in the attack range, so there's a 1/3 chance of hitting either of them. So it's just 1 over the size of the attack range. In this case, specifically, the probability of hitting some element in the attack range is 1/3. So for example, let's take a look at the attack route shown in the clip. We have a 1/3 chance of taking this route from 15 to 10, a 1/3 chance of taking this route from 10 to 4, and a 1/3 chance of going from 4 to death. This is just one possible way to get 3 hits. In order to get the full probability of getting a kill in 3 hits, we have to take into account all the possible ways that a kill in 3 hits can happen. But this is simple, because we already know that the probability of this happening at any one time is just 1/3 3 times. And in general, this is just 1 over the range to the power of n, where n is the number of hits to kill that we're interested in. In this case, it's 3. Okay, so this is the probability for one route. All we have to do now is add up all the times that we can get a kill in 3 hits. And so just by looking at this, at the probability tree, we can kind of count. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 3 possible ways to get a kill from 4. 10, 11, 12, 13, 14, 15, 16, 17. So there are 17 ways to get a kill in 3 hits. I'm just going to make a new function called omega. This is called a multiplicity function. So the multiplicity of getting a kill in 3 hits is 17. So there are 17 ways we can get a kill in 3 hits, and we can do exactly the same thing for 4 hits. How many ways can we get a kill in 4 hits? Well, here, just counting all of the red boxes on the 4th level, we get 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. 30 ways to get a kill in 4 hits. However, getting a kill in 4 hits is actually less likely, because in order to reach this 4th level, we have to add an additional factor of 1/3 to our product. So in other words, if this was the individual probability of getting a kill in 3 hits, then the individual probability of getting a kill in 4 hits is 1 over the size of the attack range to the power of 4. And in general, of course, as I had written, the probability of getting an individual kill route in n hits is 1 over r to the n. But now we can just add up all the times that this happens. So since there are 17 ways to get a kill in 3 hits, all we have to do is take this individual probability and multiply it by the number of times that it happens. So in this case, going from the individual probability to the total probability of getting a kill in 3 hits, all we have to do is multiply the number of times we get a kill in 3 hits times the probability, the individual probability of getting a kill in 3 hits. But this is pretty much the framework we need to use. And just to generalize it, what that turns into, the probability of getting a kill in n hits is the number of times that the kill in n hits occurs times the probability, the individual probability that we get the kill in n hits. And we know that the individual probability is just 1 over the range to the power of n. And so this is what we should use in our average hits formula over here. So plugging everything in gets us to our final form for the expression of the average number of hits it takes to kill a monster. And that just looks like the number of hits weighted by the probability again, which is just the number of times that that kill route can happen, that the independent kill route can happen, over the probability of each individual one. And so this is our final expression, and this is the truth behind the number of hits required to kill a monster. So let's compare what we get using this method to the naive method. So to recall, the naive method of getting the average number of hits was to take our average in our attack range, which was 5, and dividing the snail's HP by that number. So if we hit our average attack, what do we get? Our average number of hits, in the naive case, is the HP over the average of our range. And this just comes out to be 3. When in reality, and real, and bar real, our real average is actually a more complicated calculation. In this case, actually following through with the math, the first 2 terms, when n equals 1 and n equals 2, omega of 1 and omega of 2 are both 0, because a kill in 1 hit and a kill in 2 hits never happens. So the first 2 terms of the sum are 0. The only non-zero terms are when n equals 3 and when n equals 4. And we can just sum those out. So when n equals 3, we have 3 times omega of 3, which is 17, over 3 cubed, which is 27. That's the first term that is non-zero, the first non-zero term. And the second non-zero term occurs when n equals 4, and so we just plug in 4 for n and omega of 4, or the multiplicity of 4, and that's just 30. As we saw, there are 30 ways to get a kill in 4 hits. And we divide that by the range to the power of 4. 3 to the power of 4 is nothing but 81. Finally, completing this sum, we get a value that looks something like 3.37. So, as kind of expected and suggested by the form of the probability tree, we get a value that's greater than 3. And just to remind us, this is what we expect because there are many cases where we get a kill in 4 hits. So there's no way that our average can be 3 if our only possible ways to kill are in 3 and 4 hits. So this is what we wanted. This was the truth. And just to visualize why the naive guess is a bad one, we can look at our probability tree again. Essentially what we're saying when we take the average of the attack range is we're saying, okay, let's just choose our attack to be 5. And if that were the case, then only one path is picked out. We get 15 to 10, 10 to 5, and 5 to 0 here. And of course, now we can see that we're missing all the other paths. All the other information is just thrown away if we make this naive choice. And so that's why we need a sum over all paths, an ensemble average over all possible ways to kill. So now, in principle, you can calculate the average number of hits it takes for you to kill any monster. This then allows you to figure out the average amount of XP per hit for all monsters. You can then compare all these values, and the monster which yields the highest XP per hit will be the most efficient mob to grind on. Maplestory is effectively solved with this insight. But now for some caveats. Obtaining the multiplicity function for any hit tree diagram is notoriously difficult. I could not derive an analytical expression for the multiplicity function, and any related problems in pure mathematics that I could find also don't have any exact analytical solution. In other words, the multiplicity function will virtually always have to be constructed numerically. Secondly, this derivation follows the simplest possible case. It disregards skills, critical hits, damage nerfing, and all other things. But all of that can be easily accommodated for in the formalism. The key point is that we have to think about Maplestory as a stochastic game with well-defined probabilistic events. With this in mind, we can always construct a generic expression for the average number of hits to kill. Even in these more complex cases, the multiplicity function can be obtained numerically just as easily. In summary, to find the most efficient monster to kill, you have to take all possible ways of killing each monster into account. Specifically, the ensemble average over all ways to kill gives you the average number of hits it takes to kill the given monster. Realistically though, you would need to use a computer program to calculate the corresponding multiplicity function. I actually did make such a program. It's called Many Worlds, and I might make another part to this episode where I introduce it. But for now, I hope you enjoyed finding out the truth about Maplestory.